All right, so does anyone have any questions, comments, concerns about the class, about the material, about the final, anything? I made you guys something really cool. Well, I think it's cool. You guys might not think so, but so someone asked, do we still have any more weekly assignments? I'm not sure. Dr. West has been like uploading them kind of like in chunks. So I don't know if he's gonna upload more or not. But I would guess you're gonna have one for chapter 18, and one for 17. So someone asked, can we expect to see a lot of multi-step questions on the final? So not really. I'm going to look at some more practice problems for chapter 17, 18, and possibly 19, but it's not really a lot of multi-step as much as it is understanding concepts from chapters, like the older chapters, and kind of putting everything together, which we're going to work on in SI. So not as if there's going to be a couple multi-step, but it's going to be more so focused on like taking concepts from like chapter 12 and understanding how that goes with chapter 16, that kind of stuff. And then someone said, how much more extra credit will he be giving? Not 100% sure. What I've been telling you guys is usually he has 10 to 20 points of extra credit, and usually he gives an extra credit practice final that's worth approximately 10 points. Not 100% sure if he's going to give that to you guys this semester, but he almost always does. And then, yeah, so there's not like a lot of multi-step stuff. It's not too bad. And then someone said, not about Orgo, but how do you feel about biochem? Biochem is cool. I can give you more advice on biochem like the last session of the semester, just so we're done with material. You guys are kind of chilling, and we can just kind of chat about that. But biochem is usually bio people like biochem more than Orgo. I like them both. You just have to remember Gen Chem 1 stuff. That's the biggest thing. Yay! Okay, so it's working now for me. I hope you guys can see the agenda now too. Yes? Yay. All right. So I'll give you guys a chance to ask more questions in a second, but I do want to let you know that I made you guys something called a What to Study guide. So essentially, I put together a bunch of questions, or not a bunch of questions, a bunch of topics from the whole semester, and I made it into like one review guide, and I'm going to send that out to you. I just have to do the chapter 18 section. I haven't done that yet, but we're going to look at it right now so I can kind of answer all your questions about how to go about studying, what to go about studying, things like that. So can you guys see that, or did it kind of just shut off? Yes, yeah, okay. So, basically, I put a little disclaimer here saying that, you know, even though I'm the SI leader and I know a lot of things, I don't know everything, and you guys are each individuals, you know how you study best. This is just like a general overview of the semester and kind of a little guide to help you guys study. So we already went over the chunks before. So chunk 1 is chapters 12, 16, 17, 18. Chunk 2 is 13, 14, 15. And chunk 3 is 9 and 11, because that's all that random stuff that kind of didn't go along with anything else. So basically, I've broken it down by chunk and then by chapter. So for example, this is chunk number 1, chapter 12, and it goes through oxidation and all the main points of oxidation that you have to know, and then reduction and all the main points of reduction that you have to know. Things like, what's the difference between a primary and a secondary alcohol? What's the difference between a weak and a strong reagent? Things like that. And then also the Grignard reaction. hopefully now that we've done these nucleophilic additions and substitutions, you guys kind of have like you understand the Grignard more now because it's just a nucleophilic attack. The Grignard reaction has. Oh, someone said it's really lagging. So I'll give it like one more second while I talk out loud, and then if it doesn't load, I'll change the Wi-Fi, so it'll hopefully work better. This is so disappointing. Alright. That's fine. Okay, while that loads, other things you guys have to know about Chapter 12, concept-wise, when you compare Chapter 12 to Chapter 16, look at the similarities and differences between the reactions, about acids versus bases, about nucleophiles and electrophiles, and the biggest thing that I want you guys to pay attention to is the different kinds of reagents. So we're going to go through this on the last day of SI, and I'm going to help you guys make a really huge table with all the reagents we've covered from the beginning of the semester to now. And so hopefully that'll help you guys keep track of all the reactions so it doesn't feel like there's a bajillion things going on. I don't know if it just freaked out for you guys, but it kind of did for me. So, yeah. All right. And then, like I said, once you go to like chapter 16 and 17, mostly just know like what the different catalysts do, know like the different reaction names that we talked about, know how to name the different things we talked about, know how to do the reaction mechanisms. I say this a bunch of times in the actual study guide thing, but know how to do the reaction mechanisms, practice it a couple times, but when you're doing the exam, you don't really want to be doing mechanisms. You want to already know how to do things, so you're going through it super quick, so you're just doing reagent and product. So even though I like the mechanisms and I want you guys to know them, on the exam you should be focusing on looking at the reagent and knowing the product. I'm not going to bother going back to all the other pages because it's like a 20-page document. I'll just send you guys this, but I just wanted you guys to see the layout. If you guys have any questions about what this is, how to use it, what the layout is, anything like that. You're very welcome. Honestly, the reason I made it is because I downloaded this like flashcard thing off Etsy, and I was like, this looks so cool, and then I was like, I know what to do. Make a study guide. Yes, it's for Notability. So I will send this out to you probably tomorrow-ish. I just have to finish that chapter 18 stuff, like I said. So I'll give you guys a couple more seconds to ask any questions you might have. And then if you don't have any, we can go ahead and go into chapter 17. So I still use Notability, but the thing I downloaded was like a PDF that you can upload into Notability, and it's like hyperlinked. So it's like flashcards, so that you can write on it, and then you can click a button and it takes you to a different card, and then you can write the other thing. I've also heard that GoodNote is really helpful. Or OneNote, I heard that's good too. But okay, so it seems like this is finally working now. So let's go to chapter 17. And today we've basically covered all of the conceptual stuff. We did lactones and lactams. We did making and breaking those. We did order of reactivity. carbonyls. We also did naming esters, and then we did the reaction mechanism. We did the short way and the long way. Someone said it's still lagging. I don't understand why my laptop or my iPad is being stupid. We'll give her one more second. But this part, we're just reviewing concepts verbally anyway, so it's okay. So I want you guys to tell me, how does an acid catalyst affect a reaction? One person said it, but I want like one or two more people to say it, please. It makes the electrophile more electrophilic. Awesome. So an acid catalyst makes the electrophile more electrophilic. And how we do that is by protonating the carbonyl. Awesome. So then how does a base catalyst affect the reaction? What do you guys think? What does a base catalyst do? It makes the nucleophile more nucleophilic. Awesome. Start recording once more, and we should be good. Cool, sweet. So I forgot exactly where it started cutting off, but essentially we were just doing a quick concept review before we started doing examples and stuff. So the last, and someone asked if I'm recording. Yes, I am recording. I don't know if the recording is going to be like what I saw on my end or what you guys heard with like the cutting up voices and stuff, but I'll look it over before I post it. So yes, the last thing I wanted to go over like conceptually is that in nucleophilic substitution reactions, we always want to go from more reactive to less reactive. So we would like to always make a more stable product than what we started out with. So that being said, let's go over, did we do these two yet or no? I don't think we did, but okay, cool. So we're gonna do the first like 3-ish examples with the reaction mechanism. So we're kind of gonna do it the longish way. So for the first one, remind me what this is called, please. Acid chloride, perfect. So when acid chloride reacts with an alcohol, first thing we have to notice is that we have our OH minus, and so that is a base catalyst. And you guys told me a minute ago that a base catalyst is going to start the reaction by deprotonating the nucleophile. So now we have a better nucleophile. We didn't do anything to the carbonyl though. We are now reacting with this guy. And now we have H2O. Right? So when this nucleophile attacks, it will attack the carbonyl carbon, kick these electrons up. And I've said this a couple times, but I'll say it one more time. When we do these kind of additions or substitutions, the nucleophile is going to add to that carbon, right? It's very important that you guys add from the heteroatom side. I have so many people who will add from the carbon side, but we're not going to do that. You'll get the wrong answer if you do it that way. Always, always, always add from the heteroatom side. So if we do it like that, in the next step, we have O minus up here, and we added our O with an R group. So we have a minus charge. What are two things that we can do to get rid of that charge? We can do some kind of proton transfer, or we can reform sp2. Awesome. So if we wanted to protonate it, we could either take a hydrogen from the H2O, or in the past, we've had a hydrogen still on this oxygen, but we don't have that in this case. So intermolecular proton transfer is not an option. But someone else said we could reform sp2 and reform the double bond. So someone remind me, why do we like to reform sp2? Why in any case would we do that rather than just protonate? Because sp2 is more stable. Awesome, perfect. So we are going to bring those electrons down, and we're going to kick off our leaving group. So both of these could be leaving groups. Do we want to kick off the oxygen or the chlorine? What do you guys think? Chlorine, because chlorine is a better leaving group, and because if we kick this off, we would be going backwards. So at this point, we reformed our double bond to the oxygen, and now we have O and our R group. And so what's this functional group called? Ester. Cool. And in this chapter, we actually learned how to name esters. So let's practice that one more time. What is this group called? Ethyl. And I saw someone had a question. I'll go back and look at it after we name this. I'm not ignoring you. What is this group called? Ooh, we got a split. But most of you guys, yes, okay. It is an ethyl, exactly. And I was gonna yell, but you guys got it, so I don't have to. Remember that this is 2 carbons, not 1. I know a couple people said methyl, but everyone always forgets that carbon. Please do not forget her. She's doing her best. Okay, so we're gonna have F, and then what is our suffix going to be for an ester? Oh wait, exactly. So we're gonna say FN. Oh wait. Perfect. If I had a gold star, I would give it to you. All of you. Okay. Any questions on the first example? This one is a pretty straightforward and pretty quick mechanism compared to the next one that we're going to do. And I hope that didn't scare you. Okay, no, actually there was a question and I skipped it, so I'm going to go back to that. Okay, so the question was, is an acid or base catalyst always needed for these reactions? So in the last chapter, we knew that like it sometimes depended, like sometimes you need acid versus sometimes you need base, but we knew we always needed some kind of catalyst. It's the same kind of situation here. You can use either acid or base or H2O or something, but you usually do need at least some kind of catalyst in order to make the reaction happen. And then someone asked another great question. Is there ever going to be a chance or a case where we don't add this and before the 08? So I believe, I don't think so. And the reason I say that is because that's just kind of the way we do things in IUPAC. I don't know if that makes sense, but like we know we have a methane, right? And so when that is going to be before the parent chain, we just call it methyl. So we exchange that for the YL. And then whenever that is going to be part of the parent chain, and that parent chain is an ester, we swap that YL for an AN. So unless there's something super weird going on, that's usually going to be the ending for your carbon. So it'll be ethan, methan, propan, butan, like that. Cool. So this next one, I'm going to add an extra page here, and I'm actually going to do it on that extra page because I know I'm going to run out of room. So while I draw it out, please tell me what this is called. One person said it, but I want like one more person to say it. Yes. Okay, so I got two answers, which is perfect. Some people just said anhydride, which is 100% correct. That is this functional group. But some people also said acetic anhydride, and that is the perfect answer because this molecule specifically is the acetic anhydride because it has a methyl and a methyl. So perfect. And when we react acetic anhydride with an amine in acid, we know that the first step is going to be protonating, right? Is there any difference between these two carbonyls? No. Perfect. I'm going to choose this one just because that's how I like to do it. So we're going to protonate. Once we protonate, we have that wonderful positive charge. Does anyone remember what Dr. West likes to call that step where we give our oxygen a plus charge? This is like a chapter 11 thing. Yes, someone got it. It is the activation step. He always calls it that when we're talking about ethers. So if you ever see activation, that's what he's talking about. Perfect. All right. So our nucleophile is now going to use that lone pair to attack the same carbonyl that was protonated. That's important. So it doesn't matter which one you pick as long as you stick to that one. So now I'm actually going to change my arrow so that it's pointing downward because I don't have enough space. So now we have a big, ugly, complicated thing going on here. So we have an OH. That OH no longer has a charge because it's already protonated. And now attached, we have N with two H's and an R group. So charges, where are they? What are they? Please tell me. I already told you that the O is neutral. Yes, so the nitrogen has a plus charge because it has an extra bond. Exactly. So what can we do at this point if we have a plus charge on the nitrogen? A proton transfer, exactly. So what is going to take the proton? We know it's going to be an oxygen, but do we think it's oxygen A or oxygen B? Who's going to steal the hydrogen? What do you guys think? Okay, so one person says oxygen A will take it because that gives us an amide. And it seems like a couple people agree because a couple people also said A. So if oxygen A steals the hydrogen, gives those electrons back, now we get this bad boy, right? And we also can't forget about our nitrogen, which is now neutral. So now that we have a plus charge here, what are we going to do with that? Why did we give it a plus charge? It's going to be a leaving group, okay? So if these electrons come down, kick off the leaving group, now we get, and I know I'm drawing it in a weird way, but there's a method. So now we have this thing. How do we feel about this thing? Good, bad, WTF is this? How do you guys feel? Not good. I would have to agree. I don't really like how this thing looks, but that's okay. This is how we learn. So now let's try it the other way. Let's try oxygen B taking that proton. Right? So if that happens, we get a plus charge here. Ooh. We also have an OH. And now we have our handy dandy nitrogen. Always coming in clutch. So now what are we going to do? What do you guys think? Now that we have the plus charge here. That can leave. Cool. So now we have to make another decision, right? We have two different heteroatoms that can donate electrons to form a double bond and kick off the leaving group. We have A or B. Who do you think is going to donate their electrons and reform the double bond? Nitrogen or oxygen? One person answered, but I want a couple more people's opinions. Remember, I'm never gonna bite you because you said an answer wrong. This is a safe place to learn. Awesome. So a couple more people answered A, and I would agree. And so in the next step, I'll erase the A and B just so nobody gets confused. Oxygen is going to drop the electrons, kick off the leaving group. Bye-bye. So now we get don't forget that extra hydrogen. So, are we happy with our final product? No, because we have to deprotonate. Awesome. I didn't draw that plus charge here, and you guys caught on. So I believe we had HCl. Yes. Sorry for zooming in and out. We have Cl minus left in solution. So that's going to come by, pick up that hydrogen, give those electrons back. And now our for real final product is this. Oh, wait, just kidding. Ta-da! And this is an amide. And then someone asked a question. In the textbook, for some of the reactions, they said that instead of intramolecular proton transfer, another mole of amine would deprotonate the N+. Does this work too? Absolutely. So I believe I've said this at least once before, but these reactions often have multiple ways that you could write them. So there's always a million things going on in a solution. So there's usually 2, maybe 3 or 4 different ways that a reaction can and will proceed. I usually try to just pick whatever's the easiest way to draw it out for you guys. But the textbook does show you a couple different ways that it could proceed. All of them would work. I just like to draw it in the way that I think is simplest for you guys, if that makes sense. And the follow-up question to that was, we won't have to select one of them for the exam. No. So the reason I can just pick anyone to show you guys is because you guys will not be asked about mechanisms on the exam. You're just going to have to do reagent and final product. Cool. All right. I know this was super long, and just so nobody gets confused, I'll put an X here so you guys remember we didn't like this answer.
Question.
Yes.
Okay. So, just a question. these are the problems where you said that we could just like cut off the O and then add the group from the top. Is that this kind of problem?
Pretty much. And so we're essentially going to go through how to do these super quick instead of doing the long way. But you're absolutely right.
Okay, because I was looking at the answer and I was like, I feel like this could have been done easier. Okay.
And that's exactly what I was hoping someone would say. So thank you so much for saying that. Because as they said, we just did this whole reaction. It was long, it was annoying. There were so many different points where we had to pick things and it could have gone wrong. Instead, sorry, it scrolled too much. Instead, we can just do the rosemary method, cut that off, add this guy. And so we cut off this group, add the nitrogen. Now, the only thing you have to remember is the hydrogen's included here. You're just going to have to get rid of one so that it will be stable. So I'll do an X there, and you get one hydrogen left. Ta-da! So I'll zoom out so you guys can see all of that in one screen. I'll give you a second to screenshot, take it in. Someone asked a great question. How do you know where to cleave? So hopefully, okay. So I can just look at it and see, oh, this is where we cleave it, right? But that's no good for you guys because I'm not taking your exam for you. So that's why I put as many problems as I could possibly think of so that we do it a million times. So you guys get to a point where you can just see it and know automatically where to cleave it. So let's do a couple real quick. So this is the next page of the handout. So, rosemary method. This is how I like to go through it. First of all, what's the leaving group? Bromine, cool. So we're going to do that. That's where we cleave it. What's the nucleophile? And I want, yes, ethanol is a nucleophile, but which atom specifically is the nucleophile? Oxygen, cool. So I'm going to do an arrow right here. And we know we get rid of one of these hydrogens. So our final answer will be, wow, that was ugly. We attach the oxygen with two carbons attached. So let's do the next one. What's the leaving group? Chlorine, cool. So bye-bye chlorine. What's the nucleophile? Sulfur, cool. And we're going to get rid of a hydrogen here. And while I write that out, I forgot to send you guys the sign-in sheet, so please fill that out when you guys get a chance. But okay, so we know sulfur is our nucleophile, so we add the sulfur and we add our methyl. Next up, I'll try to keep them all in frame. All right, so now we have a big, ugly looking one, right? What's going to be the leaving group, the OH or the pH? So the benzene ring, the phenyl. The OH, and that was a really quick answer, and that's awesome. And I think the reason they knew that it would be the OH automatically is because we can break carbon-oxygen bonds. We're not going to break carbon-carbon bonds. We don't like to do that. So this guy is going to leave. Who is our nucleophile? Oxygen, cool. So this guy. And we cancel out one hydrogen. And so our final product will be bam. just for funsies, let's name this ester. First things first, what's this group going to be called? Ethyl. What is this thing called? Phenyl. While that's true, we're actually just going to stick with benzene for now. So it's going to be benz and, just because that's kind of a cleaner way to say it. Bands and what's the suffix for an ester again, please? Oh, wait. Awesome. You guys are pros. I'm so proud. Alrighty. So we just did 3 examples in like, what, 3 minutes? That was awesome. You guys did great. So how do you feel about the quick Rosemary version of how to do this instead of doing the mechanism every time? Good. People are saying they like it. Awesome. So I don't try to scare you with the mechanism. It's obviously important. You guys should practice it. You should look over it. But it is kind of terrible and terrifying, especially the first couple times you do it. So while I urge you to look at it at least a couple times just to know what's going on, when you're actually taking the test and doing practice problems, you guys should probably do it this way because that'll save you a lot of time. Alrighty, so that's okay. We can do the rest of the handout on Friday. Do you guys have any questions, comments, or concerns today? Sorry about the technical difficulties again. But I hope you guys enjoyed the almost picnic. And someone asked a really great question. They said, just to clarify, these examples are all called nucleophilic acyl substitutions. Yes. So we're only going to give 2 of these reactions specific names. It's not going to be like chapter 16. And we will go over that on Friday. We just have an esterification. And again, we'll go over that Friday, but just in case you guys were wondering. And I'll send out the thingy one more time because I forgot to do it. That's all I have for you guys today. If any questions, let me know. I'll stick around for like 2 more minutes in case anyone has questions. But if not, I will see you on Friday. Says goodbye as well.